Okay, 2.5 video number 2. So we've been talking about the chain rule and how to apply the chain rule for derivatives. And one of the questions was, if you see something, like if we see something that had a product rule or a quotient rule and it had a chain rule on it, how are you going to necessarily know which one is first? So we're going to do some more examples, and hopefully this will start to make a little bit of sense. So if I look at this first function, y equals the quantity 3x minus 1 over x squared plus 3, all squared. If you listen to the way I actually just said that, the quantity came first. Okay, it's a big chain rule. Inside of the chain rule, you should be able to clearly see that there is a quotient rule. So in this case, we actually have to apply the chain rule first, and then when we do the derivative of the inside of this, that's when we actually apply the quotient rule. So it really is just recognizing what the main part of the function is. Is it a product first? And within the product, I'm going to have to apply the chain because I've got a composite as one of my two functions. Or is the whole thing a chain because it's a huge composite function, which this one is? So that's what we're going to have to do here. So we're going to apply the chain rule first. So the chain rule, once again, says you're going to do the derivative of the outside piece, which is the something with it inside, squared. So we're going to bring the 2 out to the front. We rewrite the composite piece, and then reduce the power by 1, so it's now the first power. We typically don't write the 1 as a power anymore because it'll look like a prime symbol, and we don't want people to think it's a derivative. So it's 2 times that whole thing to the first power times the derivative of the inside. Now we need to apply the quotient rule because the derivative of the inside is a quotient. So if you want to think about it in this way, we've already applied the derivative of the outside, so all of this is now done. Now we have to do the derivative of that inside. So the derivative of the inside, quotient rule, derivative of the top is 3 times the bottom minus the derivative of the bottom, 2x, times the top, all over the denominator squared. Okay, and this obviously could clean up. One thing I just want to make sure that you see, if I were to take that x squared plus 3 from the first one, and I were to multiply it by the x squared plus 3 squared from the second one, I would then get x squared plus 3 cubed in the denominator. And then you could distribute all of that, combine like terms, multiply everything out on top. We're not going to do all that. I just wanted to point all that stuff out to you, that this could be cleaned up. It actually gets to be pretty long and messy in this case, but it could be done, and there will be reasons for us to do that in the future. I'm going to go ahead and erase all those extra marks because we are finished with the problem. So that is your derivative. Okay, it's not a pretty one right there, but it is the derivative. Now let's talk about trig functions. Trig functions, unless it is just sine of x, cosine of x, or sine of theta, or cosecant of theta, or something like that, and technically those are even chain rules in themselves, they're all going to have some kind of a chain rule. Now, it does help if you understand that 2x right there, that's the angle. That's sine of 2x. It's not sine times 2x. It's sine of 2x. You have to take the sine of something. That's the angle. So the angle itself, in this case, is a composite. So we're going to do exactly what we did before. The outside function is the sine function. So we'll take the derivative of sine, which is cosine. The angle doesn't change, but we have to multiply it by the derivative of the angle, in this case, which is 2. So then we get 2 cosine of 2x. That is your derivative. Okay, same general idea for the next one down. If I take the derivative of cosine of an angle, it's going to be the negative sine of that angle times the derivative of the angle, which in this case, the derivative of x minus 1 is 1. So I don't really need to write anything else. That one's done. Okay, one more down here with tangent of 3x. Hopefully by now you're starting to get the idea of tangent. So the derivative of tangent is secant squared of the angle multiplied times the derivative of the angle, and the derivative of 3x, of course, is just 3. So we could clean that up to be 3 secant squared of 2x. Okay, not too difficult, at least not yet. What if, and I'm going to write this one as an extra problem, what if we did y equals, and we'll start off with a relatively easy one, sine to the 4th of 5x. Okay, so now I've included something that we haven't seen before. Remember that sine to the 4th is just another way of writing sine of 5x, the whole thing, to the 4th power. What it really means is sine of 5x times sine of 5x times sine of 5x times sine of 5x. We put the 4 in between here as a shorthand notation so we don't have to write those extra parentheses, but that's what it means. It means sine of 5x times itself 4 times. There are 4 factors of sine of 5x. So by writing it the second way, like I did right here, you can clearly see that there's a chain. Technically, there's a chain of a chain of a chain in this case. So you have to be careful. You have to follow your steps. So y prime here, bring the 4 out to the front, reduce the power by 1. I'm going to go ahead and put it back in between. Okay, so now I am done with this part. Now I have to take the derivative of sine of 5x. But once again, that's another chain rule. I have to take the derivative of sine like we did in a couple of steps before, which is cosine. Again, the angle doesn't change. So now I'm done with the sine part. Now I have to take the derivative of the angle, which is 5. So technically there was 3 steps in that one. I'm going to go ahead and clean this up. It's going to be 5 times 4 out in the front, which is 20. Sine cubed of 5x cosine of 5x. That is your derivative. So I like to tell people when it comes to trig functions, you treat it as PTA. You deal with the power first. So if there's a power, in this case there was, the power was the 4th power, then you deal with the trig, and then you deal with the angle. So it's the derivative of the power part first, then the trig part, then the angle, multiply them all together. Okay? Now I'm going to try and explain this next one the best that I can. If you understand it, great. If not, I'm still going to give you a way to be able to figure all this stuff out. Okay, so a couple things. We need to recall, and this is from trig, this is from probably pre-calculus, that e to the natural log of a is the same thing as just a, because e and natural log are composite functions, are inverse functions of each other. When you composite them, you end up with the argument, which is what we just got there. So e to the ln of a is a. Okay? We could rewrite a to the x as e to the ln of a to the x, because again, they are composite functions. We're compositing inverses. So a to the x is the same thing as e to the ln of a to the x. We could then use log properties, or using log properties, we could state that this is equivalent to, so I'm going to actually write this down here, e to the x ln a. And you might ask yourself, well, wait a minute, what did you just do there? I brought this x out to the front of the natural log, because if you have an exponent on your argument, you can bring it out to the front of the natural log. That's one of our properties. Okay, we're actually going to call this, or this is actually going to become u, where the u, let me start that over again. we are going to say that u is the exponent, which is the x ln of a. So we're basically going to put this into a composite function where we're going to have e to the u as the function, but u itself is x ln of a. So hopefully you can see that if I took that and I put it here, I would get e to the x ln of a, which is the same as e to the ln of a to the x, which is the same as a to the x. So I've kind of backtracked all the way back to this right here. Okay? If you're understanding all of that so far, then let's go ahead and see how the chain rule applies to e to the u. So if we were to take the derivative of e to the u, remember that the derivative of, in this case, if it was e to the x, it would be e to the x. Well, this, we're taking the derivative. We want to find, I guess, d du in this case. And then we want to multiply that by du dx. Okay? So d du, or the derivative of this with respect to u, is e to the u, multiplied by the derivative of u with respect to x. Remember that ln of a, that's just a number. Whatever a is, it's just a number. It's a value. It's like ln of 5. So x times some number, or 5, let's just say it was 5 times x, the derivative would be 5. Since this is ln of a times x, the derivative is ln of a. So that's times ln of a. Okay? If that doesn't make any sense to you, because really all I've done is I've created a chain rule here for us. If that doesn't make any sense to you, this is probably the easiest way. I just wanted to show you where all this came from, by the way. This is probably the easiest way to do it. If I was going to take the derivative of an exponential function where the base is constant and you have some kind of an exponent which is a variable, so some kind of function of x, it's a 3-step process. The derivative of every exponential follows these same 3 steps. First step, simply rewrite the function. So the derivative of an exponential will have itself in the derivative, always, times the natural log of the base. And in this case, the natural log of the base is a, or natural log of a, multiplied by the derivative of the exponent. 3 steps. Let's put this in regular terms. So the first thing we do is we rewrite the function. The second one, it's the natural log of the base. And then the last one is the derivative of the exponent. So let's rewrite it, times the natural log of the base times the derivative of the exponent. Every exponential works that way. Okay, so now let me go ahead and show you, because we already know that the derivative of e to the x is e to the x. Let's actually see that that works using this pattern. So if y equals e to the x, and I want to find y prime, the first step says to rewrite it. That's e to the x. Times the natural log of the base, natural log of e, times the derivative of the exponent. The derivative of x is 1. The natural log of e is also 1. So what you get is y prime equals e to the x times 1 times 1, or y prime is e to the x. Still, I think one of the coolest functions. The derivative of e to the x is itself. There's just a lot of really cool things that you can actually do with that. All right, but now let's try and apply it to one that's not e to the x, because that is the only one that works like that, where the derivative of e to the x is e to the x. All the other exponentials are going to have something other to it. It's going to follow our 3-step pattern. So y prime of 2 to the x. So the first step is rewrite it, 2 to the x, times the natural log of the base, the natural log of 2, times the derivative of the exponent, which is 1. So really the only thing you can do is you don't need the times 1, so you could write the ln of 2 out in front or keep it on the back side. It doesn't matter here. 2 to the x times the ln of 2, and since the ln of 2 is not a nice number, we leave it as the ln of 2. That's it. That's the derivative of that exponential function. Okay? and we will see more exponential functions, but really that's what you need to know. They're not that difficult to do. Okay, let's do a little bit more practice with some of our trig. So where the parentheses are located in this case is extremely important. So you've got y equals cosine of 3x squared. So the 3x squared, that is clearly the angle. It is in parentheses. That's the composite function. So we can do y prime equals, remember it's PTA, power trig angle. I have no power of my cosine function. The only power that's in there is within the angle. So that's not a power of the trig part. So there's no power to worry about. So then it's trig. The derivative of cosine is the negative sine. Keep the angle. Angle never changes. But then we do have to multiply it by the derivative of the angle, which is 6x. So we'll write that as negative 6x sine of 3x squared. Notice where the parentheses are in the next one. The cosine of 3 is separated from the x squared, and that's purposefully done. Cosine of 3, if you actually just plug cosine of 3 in a calculator, it's just a number. So it's like having a 5 out in front of the x squared. This is just a straight power rule, which says that I bring the 2 out to the front and reduce the power by 1. So the derivative is actually 2 times the cosine of 3 times x. Or you could write it as 2x cosine of 3. Cosine of 3, again, is just a number. It's a coefficient. So don't be fooled by that. The parentheses placement was important there. Okay, and then as you can see in these last couple, now I actually have exponents on my trig functions. So for the first one, do the power first. So y prime is going to be 2 cosine of 3x. Okay, I'm done with the power. Get rid of that. Now I multiply that by the derivative of the trig part, which is going to be the negative sine of 3x. Okay, done with the cosine part. Now we multiply that by the derivative of the angle, which is 3. Okay, and again, I'm going to clean this up. I've got a 2, I've got a negative 1, and I've got a 3, all coefficients. I can multiply those together and get negative 6 cosine of 3x sine of 3x. And that's your derivative. Okay, last one on this page. This will probably be the last one. We'll finish up with one additional video. So we've got f prime of t. Okay, deal with the power. Bring the 3 out to the front. Reduce the power by 1. I'm going to put the 4t in parentheses. Just for me, it's easier to see that way. Times. Okay, I'm done with the power. The derivative of sine, which is cosine, 4t. Done with the sine part. Now deal with the angle. Derivative is 4. So cleaning that up, we get 12 sine squared of 4t cosine of 4t. That's your derivative. I'm going to go ahead and erase all those marks so we know what the original problem was. You probably should not completely scratch these things out, by the way. Cross them off or something, but don't scratch it out completely so you don't remember what the original problem was. Okay, that's plenty enough for this video. We will come back with one final video and put some application to it.